Hi everybody, I'm Jolan Philippe and I'll present Executing Certified Model Transformations on Apache Spark, a work we made in collaboration with Massimo Tisi, Hélène Coulon and Gerson Sunier as a part of the Locomod project. Let's start with a bit of context. The purpose of this work is to propose a solution for reasoning on large model transformation. For those who don't know what a model transformation is, a model transformation is basically the creation of the modification of an existing model. So, in one side, correctness is afforded by formal proofs of contracts and the output of the transformation. And in the other side, to meet large model challenges, the solution must be scalable, both in terms of resources and in terms of the size of the model. Second, also handle with memory overloads, and also return a result in a decent amount of time. In model-driven engineering, there exist solutions based on the query-reward correspondence designed with proof assistance to formally reason on models and on transformations. For the big model challenges, there are also solutions based both on hardware solutions and software solutions. So hardware solutions are solutions involving multi-core or distributed architecture, usually along with software solutions to ease the parallelization of the work. However, there's no bridge in these two research areas. So the goal of this work is to build a bridge between correctness and larger model transformation. So as the basis of the work, we started from CocTL, a DSL designed for expressing transformations, written with the proof assistant Coq. CocTL allows user to formally reason on properties defined for a given transformation. But Coq is not made for executing code, just for reasoning, especially the former CocTL specification. As a distributed solution, to meet with the large model challenges, we use Spark, a Scala framework for data analytics. To explain a bit more about how Spark works, it follows a master and worker architecture, where the master will coordinate all the workers for a job. Contrary to a Hadoop solution, Spark only does in-memory computation, where Hadoop will write on files between two computations. In Spark, parallelism is performed on distributed lists that have the same primitive functions than sequential lists, for instance, the map, the reduce, flatten operators. But one of the key aspects of Spark is the high level of confidence we have in the solution. In terms of semantic preservation, when we use distributed lists of sequential lists, we expect to have the same semantic. Also, it's very owned by the large community. It's a framework widely used by data analysis, so we trust in Spark. It's a key aspect of the work. So the global objective of the work is to bridge correctness from the Coq world to a distributed solution with the Spark world. So to do that, we have now in Coq two distinct specifications. The first one, the one which existed before, designed for reasoning, referred as CocTL, and a new one for the actual execution on distributed architecture, specifying the optimizations we made for the target solution. It will be referred as parallelizable CocTL in the rest of the presentation. We also made a proof of equivalence between those to be sure that the CocTL specification does the same than parallelizable CocTL. So reasoning on CocTL will all the proofs made on CocTL will be also true on parallelizable CocTL. And then at the end, we have an executable solution on top of Spark called SparkG for Spark Transformation Engine. So how did we proceed? We had user theorems certifying CocTL transformation running on CocTL. So we refined CocTL with the new specification called parallelizable CocTL. And then we extracted all the parallelizable CocTL engine to an executable engine on Scala. So we extracted by hand the code from parallelizable CocTL to Scala transformation engine. And to finally obtain a solution working on Spark, we replaced all the data structures in Scala TE by a distributed list to have a solution working on Spark. And then we obtain the solution Spark Transformation Engine. About the transformation itself, to form a cocktail transformation, the rules of transformation for the transformation are also translated by N to a Scala transformation. The level of confidence we want to have, the high level of confidence we want to have is on this part. And I will give you in a moment some details about the confidence level of these 3 steps. So first, the parallelizable cocktail is a refinement of the first specification designed to increase parallelization. For the confidence on this part, we made a formal proof of equivalence between the 2 specifications. For the second part, the extraction of a parallelizable cocktail into Scala code, we made it manually using only pure function. So it means all the functions we had in cocktail were pure functions, and we have the exact same ones in Scala using even the same syntax and the same algorithms. For the last step, we replaced all the sequential data structures by distributed data structures, in this case lists, to obtain the Spark TE solution. About the confidence, we trust in Spark, so we are pretty sure that all the processes in Spark are equivalent to sequential work in Scala. For the rest of the presentation, I will use a small example to explain how the algorithm works. So let's consider a table to column model that we want to transform into a class and attribute model. So we have 2 rules, one for the table to class. Each table will be translated into a class, and every column will be translated into an attribute. But for the second rule, we also match the table to know what is the owner of the column, and then to recreate the links, we will resolve on the second matched element the owner of the target attribute. So how does it work? First, the tuples, all the tuples will be created by the engine that possibly match with one of the rules. So here we have the maximum arity we have is 2, so we create all the tuples from 1 to 2 elements. These tuples are distributed using the distributed list of Spark, and they will be tested to know what element can be transformed. So in the second step, we instantiate all the output elements, and also we keep trace links for recording all the input and output elements that will be helpful for the rest of the transformation. Then, after a broadcast phase, every worker will know about the full trace links, and the goal of the second step is then, using these trace links, recreate all the links in the output model. And then in the final step, we collect the result into a final model. So the first optimization we made was to move from a one-phase approach to a two-phases approach. In the standard cocktail specification, all the transformation is made in a single phase, where a rule will generate output element and the output link at the same time. It's very easy for reasoning because you know where you keep a trace on real time of what happened. So it is easy for reasoning, but not very efficient and not parallelizable. So in the new version of CorpTL, we have a two-phases implementation, one for the output element first, and then all the output links are created from the full set of output elements. The second optimization targets the tuples themselves. In the figure I just have shown you, we generated all the tuples with a recursive algorithm. So we start by generating the tuples of one element, then from it all the tuples for two elements, and so on and so on. And we finally distribute at the last iteration the elements. However, it leads to have many useless tuples. For instance, all the tuples that cannot match any type of any rules. And then it can lead to an imbalance in partitions. In a partition, one worker can have all the tuples that match with something, with a rule, where a second one can have nothing. So to avoid this kind of imbalance, we adopted a new strategy for generating the tuples. So instead of iterating on elements, we iterate on rules to generate all the elements of type corresponding to the input of the rule. So all the tuples will at least match with the type of one rule, and then every tuple will be evaluated. The quad condition of every rule will be evaluated on at least one tuple. It leads to more balanced partitions because now we are sure that every worker does something at least. Test for every tuple the quad condition. The third optimization is the use of the traces in the standard cocktail specification to create the links. All the elements were recreated to know where the links are from. In our solution, we use the trace links in the apply phase, the final phase, to iterate on it. So the goal is to find the corresponding rules, find all the involved the output element from the other rules, and using resolving functions, we create the output links. So we don't have to recreate the output element first to create the links. That was the case in the cocktail specification. So to study the parallelization and scalability of our solution, we conducted experiments on the last version and the almost last versions of Scala and Spark on the J5K platform. That it is a communitary platform which provides different clusters on different places in France to make experiments in a research context. We targeted 3 case studies. The first one is the complete relational to class case. So a more complex, it is the example I have shown you before, but in a more complex way, because we introduce multi-valued attributes and types and so on. The second case is the IMDb find couples from TTC, where the goal is to find a set of actors who used to play together in the different movies. And the third one is a DPLP query, where the goal is to find for a specific journal what actors are active in other journals. So the target of the first experiment was to, on a simple model, see how the scalability is performed. So for the relational to class, we observe a very poor scalability, so a very poor speed up for the solution, mainly because the model itself is low, the complexity of the transformation is low, and the size of the model is small. So the scalability of the transformation is quite bad. Because of the low complexity of the case. The DBLP case has a medium complexity for the operations, so we observe a better speed up with hyper speed up here in the case of 2 cores, because we increase. So in one core we don't have enough memory for managing all the transformation. So when we increase both the number of cores and the allocated memory, because each core has a specified associated memory, we observe a hyper speed up because now the process won't write on the disk anymore. And with the IMDb case that has the highest complexity, we observe not that bad, I would say, scalability, something that is growing from 1 to 3.3. It's half of the optimal speedup we can obtain at this point, but it comforts us on the fact that if we have a complex enough transformation on a big enough model, we have a good speedup. To experiment a bit more about the potential speedup we can obtain, we introduce in the transformation some sleeping times to simulate the computation time on phases. That is, on the instantiate phase, on each rule, we, in addition to creating the elements, we also added a sleeping time, a concrete sleeping time, to observe what happens if the computation takes longer. We did the same in the apply phase and the same in the guard checking condition. So what we observe is, the introduced simulated times are from 0 millisecond to 2 seconds, and we observe how the scalability reacts to a longer computation time. So what we observe is, for a model of 150 elements with almost 300 links, if we increase the computation time on the rules, after 1 second, we reach more than 50% of the ideal speedup, up to 32 cores. With a bigger model, up to 28 cores, we see that with starting from 120 milliseconds of computation on the different parts of the rules, we have more than 50% of the ideal speedup. So on a big model, not a big model, but a bigger model with 600 elements and 1000 links, with a computation of 0.1 second, we have more than 50% of ideal speedup up to 128 cores. So, as a conclusion, our contribution, we made a cocktail refinement with a new specification, parallelizable cocktail, specifying the different optimizations to increase the parallelization of the solution. As an executable counterpart, we translated the cocktail specification into Scala. And finally, we obtained a parallel implementation of the executable part on top of Spark. This workflow can be adopted for other solutions. So, more than providing a solution working on distributed architecture with a high level of confidence, we also propose a workflow to have a such solution. As conclusive remarks, we have shown potential scalability with different operational costs for the tool. But we are still facing many challenges caused by memory issues, the distribution itself, and the Spark overhead. So we need to find a perfect way to manage with all these issues in future works. So concretely, at future work, we plan to write a certified compiler from Cocktail to Scala directly, instead of having to do it by hand. We would prefer to have a certified compiler to do it, to maintain the level of correctness, the high level of confidence. We also want to study additional approaches supported by Spark, for instance, GraphX, and we want to integrate the work with other solutions like persistence solution, with, for instance, HDFS solution to partition our work. Thank you very much for your attention, and let me know if you have questions.